Hello friends, I welcome you in lecture number 7 on functions. In this lecture we will define inverse functions. So first we understand the definition of inverse function and then we will discuss some examples on how to find the inverse of a given function. So suppose I consider a function from set A to set B which is 1 1 as well as on 2. For inverse of a function, our function must be 1 1 and on 2, or we can say that function is bijective or 1 to 1 correspondence. So suppose f is a function from a to b which is bijective or 1 1 and on 2, then inverse of a function is denoted by f inverse and it is function from B to A. Now suppose for element A image is B under this function f, then we know that B is equal to f of A and we are considering f inverse from B to A. So if we consider B here, then its image will be f inverse A. So if f of A equal to B, then this is f inverse B. If f of A equal to B, then f inverse B will be equal to A. If we reverse on both sides here, we can understand in this way f inverse B equal to A. So this is the way how we can find out inverse of a given function. We can simply understand by considering two particular sets A and B and considering a function from A to B which is 1 1 and on 2. For example, suppose I consider two sets, say set A and set B, and I have to consider function from A to B which is 1 1 and on 2. So suppose I consider elements P and Q here, and here I consider R and S, and the function must be 1 1 and on 2. So suppose I consider image of P as S, then image of Q must be equal to R if we want to define a 1 to 1 function. And for on to function, for every element of the codomain there must be some element in the domain which is the pre-image of this. So we can see that for R belongs to B, there exists P in A such that f of P equal to R. Similarly, for S belongs to B, there exists an element Q in A such that f of Q equal to R. F of P is S and f of Q equal to R. So this function f from A to B is 1 to 1 because two elements P and Q are having different images, and this function is onto because for each element of B there is some element in set A such that f of P equal to S and f of Q equal to R. So here f is a function from A to B which is 1 1 as well as onto. So now f inverse is defined as having domain as B and codomain as A. Domain of f inverse will be codomain of f and codomain of f inverse will be domain of f. If f is a function from A to B, f inverse is a function from B to A. So for this we can see we have to find out value of f inverse at every element of set B. So for f inverse of R, for this we can go in this way. If R is the image of Q under F, we will consider Q as the image of R under F inverse, that is F inverse R equal to Q, because f of Q equal to R, therefore f inverse R is Q. Similarly, image of S under F inverse S is equal to P, we will consider in this way. So we will simply reverse this. If f of A equal to B, then A equal to F inverse B. If B is the image of A under F, then A is the image of B under F inverse. And this is possible if and only if function is 1, 1 and onto. So if our function is not 1, 1, then we cannot define F inverse. If our function is not onto, we cannot define F inverse. And suppose our function is from infinite set to infinite set. Suppose our function is defined in this way, fx equal to y, then we will consider x equal to f inverse y. And we will see in the examples that how we can define f inverse if f is given from one set to another set and provided f is bijective. So here I have written the definition. If they ask the definition, you should write in this proper way. Let f from A to B be bijective. Another word is 1-to-1 correspondence or 1, 1 and onto. So here we are considering f from A to B, which is 1, 1 and onto. The inverse function of f is the function that assigns to every element of codomain, that is B, the unique element A of capital A such that f of A equal to B. Because we are considering f inverse from B to A, so f inverse is a function from B to A if for every element of B there is unique element from this set A. So that is the definition of function. F inverse is a function from B to A if for every element in set B there is unique element from set A such that f of A equal to B. The inverse function of f is denoted by f to the power minus 1, and we will read this as f inverse. So if f of A equal to B, then f inverse B will be equal to A. And we make this remark that if a function f is not bijective, then f inverse cannot be defined, and if function is bijective, then f inverse can be defined. So we can say that bijective function is invertible because we can define an inverse of this function. So our function is invertible if it is 1-to-1 and onto. Now we consider this example. We are given the function from set ABC to 1 to 3 such that f of A equal to 2, f of B equal to 3, f of C equal to 1. And the question is f invertible, and if it is, what is its inverse? So first we use notations for given sets. We denote set ABC, set containing ABC is denoted by capital A, and set containing 1, 2, 3 is denoted by capital B. And given that f is a function from A to B, given that f is a function from A to B such that image of A is 2, image of B is 3, and image of C is 1. So it is obvious that different elements are having different images. Image of A is 2, image of B is 3. That means images of A and B are distinct. Similarly, images of B and C are 3 and 1, they are distinct, and images of A and C are 2 and 1, which are distinct. So it is clear that f is 1-to-1. We have to check whether function is 1, 1 or not before defining its inverse. Clearly f is 1, 1. And for onto, we have to check that whether each element of B, which is codomain, is image of some element of set A or not. So we can see for 1 is the image of C from set A. Similarly, 2 is the image of A, and 3 is the image of B. So therefore f is 1-to onto also. f is 1 1 and onto. Therefore f is bijective. These are different words which we should be familiar, or we can say that f is 1-to-1 correspondence between sets A and B. So I am just writing all these things so that we can remember that all these are same words. So because f is bijective, therefore f is invertible, and inverse is a function from B to A, and such that now we will consider images of elements of B under F. So we can start from here. F of C is 1. So from this I can say that C is the image of 1 under F inverse. So here I will write that such that F inverse of 1 equal to C. Then I consider another element 2. F of A is 2, therefore F inverse 2 will be equal to A. So image of 2 is A under F inverse, and image of 3 under F inverse that we will obtain from here. F of B is 3, therefore B equal to F inverse 3. So we can see that for every element of set B we are having unique element from set A, therefore F inverse is a function from B to A, and it is defined in this way. So it is very easy to check whether function is invertible or not. First we have to check whether it is 1 1 and onto, and then by reversing we can find out the definition of inverse function. F of A equal to B implies A equal to F inverse of B. We are using this fact. We consider another example in which we consider infinite domain and codomain. Let f from z to z be such that fx equal to x plus 1. Question is f invertible, and if it is, what is its inverse? So first we write down what is given. Given that f is a function from set of integers to itself, and f is a function from z to z given by fx equal to x plus 1. Image of x is x plus 1 under function f. X is an integer. So first we check whether this is 1 to 1 or not. So we know that if fx equal to fy implies x equal to y, then f is 1 to 1. So for that we consider two elements x, y in the domain such that fx and fy are equal. So this implies fx is given by x plus 1, fy is given by y plus 1. So from this we can easily see that x and y are equal. Therefore fx equal to fy implies x equal to y, and x and y are arbitrary integers. Therefore f is 1 1, or we can write that f is 1 to 1 or injective. Another word for 1 1 function is 1 to 1 or injective. Now we check for surjective function or onto function. So we know that a function from one set to another set, we just recall a function from A to B is onto if for every element of codomain, for every y in B, there exists at least one element x in A such that fx equal to y. If this happens, then we can say that function is onto. Here domain and codomain are z and fx is given by x plus 1. So suppose f is onto, then we can say that first we consider any element in the codomain. Let y belongs to Z, which is codomain. Here domain and codomain are same. So here in the bracket we mention let y belongs to Z be in the codomain such that suppose y is the image of some element of domain such that y equal to fx for some x in the domain, which is again set of integers. So we first assume that suppose function is onto, then y will be image of some element of domain. Now if this is true, then we will obtain the value of x from the domain corresponding to this value of y in the codomain, and if this is not true, we will get some contradiction. So now y equal to fx, therefore fx is given by x plus 1, and we are interested in the value of x. So from this we obtain that x equal to y minus 1. So this x must be in the domain which is set of integers. Now y is considered from the codomain. Y is an element of codomain which is set of integers. Therefore y is an integer, and if y is an integer, then y minus 1 is also an integer. So we can say that x equal to y minus 1 is in the domain. So for any y in the codomain, we can find out x in the domain such that fx equal to y. So therefore we can write that for any y belongs to z in the codomain, for any y in the codomain, there exists x equal to y minus 1 in the domain such that if we find out value of f at this x, we must obtain y. Fx equal to x is replaced by y minus 1. Definition of fx is x plus 1. So therefore f of y minus 1 will be equal to y minus 1 plus 1, and it is y. So therefore function is onto or surjective. So we have shown that function is 1 1 and function is onto. So we can write that thus f from z to z is 1 1 and onto, or it is bijective. Therefore f is invertible, that is f inverse exists. Therefore f inverse from z to z exists. Now to define this f inverse, we can consider, suppose I consider two sets which are domain and codomain, both are set of integers. Suppose I consider x here, then image of x we denote by y, and y will be equal to fx. So we are interested in the function f inverse from z to z, and elements of codomain are denoted by y. So we are interested in the value of f inverse y. So f inverse y, suppose f inverse y is equal to some element x from the domain. Okay, if x is having image as y, then we assume that suppose image of y is x, then we can say that f inverse y will be equal to x. So from this we obtain y equal to fx, and fx is given by x plus 1. Therefore we are interested in the value of x. So x is equal to y minus 1, and this is nothing but f inverse of y. So this is the way how we can find out the formula for f inverse. First we consider f inverse y equal to x, therefore y will be equal to fx by the definition of inverse of a function. Now fx is given by x plus 1, therefore x equal to y minus 1, and x is nothing but f inverse y. So we obtain that f inverse of y equal to y minus 1. So we are just using the definition of inverse function. If fx equal to y, then we are just using this definition. If y is the image of x, then x is the image of y under f inverse. This is the definition of inverse function if f is 1 1 and onto. So now we consider let y belongs to z. Now this is domain of f inverse such that f inverse of y equal to x. Okay, we are considering this one, y in the domain of f inverse such that f inverse of y is x. Therefore, by the definition of inverse function, we have y equal to fx. Therefore, y equal to x plus 1. We are interested in the image x under f inverse. So, we find out value of x. So, x is equal to y minus 1. Now, again x is f inverse y. So, therefore, we replace x by f inverse. So, we obtain f inverse y equal to y minus 1. So, therefore, function is invertible and it is given by, therefore, f inverse from z to z exists and is given by f inverse y equal to y minus 1, y belongs to z. Now this y is a dummy variable, so if you wish you can write down instead of y you can use any variable. You can write f inverse x equal to x minus 1, x belongs to z, or you can keep this as it is also correct. So this x and y are dummy variables. If we wish we can write f inverse b equal to b minus 1. We just have to understand that image of y is y minus 1. So instead of y we can write x also, we can write b also. So in this way we can decide the inverse of a given function if it is 1 to 1 and onto. If it is not 1 to 1, f inverse does not exist. If it is not onto, f inverse is not defined. So f inverse is defined if our function is 1 1 and onto. Now we consider this example number 3. Let f from R to R be given by fx equal to x square. Is f invertible? So we have to answer this. So we know that function is invertible if it is 1 1 and onto. So first we check for 1 1. So f from R to R is given by fx equal to x square. And if you remember, we have discussed in earlier lectures that this function is not 1 to 1. Suppose we try to prove that this is 1 1, then we will go in this way. We will assume that fx equal to fy and we will try to prove that x and y are equal. So suppose fx and fy are equal, then this implies that x square and y square are equal. This means x equal to plus or minus y. So here we can see that if we had obtained x equal to y only, then we can say that function is 1 1. But here another possibility is x is minus y. So that means x and y can be different and fx and fy can be equal. So there are chances that we obtain distinct elements but their images are not distinct. So to show that this is not 1 to 1, we have to decide two elements in the domain, or we have to decide two real numbers which are distinct but their images are not distinct. So that is obvious. Suppose I consider x equal to say 1 and y equal to minus 1 in the domain which is R. We know that fx is going to be f of 1 which is 1 square, that is 1, and fy is f of minus 1 which is minus 1 square, which is 1. So we can see that x is not equal to y. So we have got two distinct elements, but their images are equal. So we require that distinct elements must have distinct images if our function is 1 to 1. So we have obtained two distinct elements whose images now are not distinct. Therefore f is not 1 to 1, and if f is not 1 to 1, f is not bijective. Therefore f inverse is not defined, or we can so say that f is not invertible. So f is invertible because if and only if f is 1 to 1 and onto. So this is all about this session. In this session we have discussed inverse functions, and we have discussed problems on how to finding the inverse of a function. So in upcoming lectures we will discuss some more things about inverse functions. I hope you like this. Thank you very much.